So my name is Klaus Mølmer. I have the pleasure of chairing this morning session. Let's just get started. Maybe a few people will still enter into the room. The first talk is given by Nechita, and I think this is, yeah, you're ready to go.
Thanks so much. So welcome back. So today it's the second of the three lectures, and the plan today is to talk about tensors, to start talking really about tensors, because up to now we just saw like more norm spaces. This was the topic of yesterday's lecture. So today I'm going to talk about tensors and also introduce the first tensor norm that in this lecture, which will be this injective tensor norm and related to the entanglement of multipartite pure quantum states. And tomorrow the plan is to talk about more generally, more abstractly about tensor norms, and then to talk about the entanglement of mixed quantum states in the bipartite and the multipartite setting. Okay, good. So tensors, what are tensors? Many things. So if you ask large language models, they will say that more or less it's a generalization of vectors, matrices up to higher order. And then if you push the LLM to be a physicist, a mathematician, or a computer scientist, then they will give emphasis on different aspects of these tensors. So for instance, a physicist will say that, you know, a tensor is something that transforms like a tensor. A mathematician will tell you about algebraic geometry, which indeed is one branch of mathematics which is very concerned about tensors. And the computer scientist will just say you that it's like an array with 3 or more dimensions. And of course, nowadays tensors are like a central object in machine learning, in large neural networks, because somehow they are used to mainly to process batches of matrices. So it's not really this point that we're interested in. So we're really not going to see a tensor like a bunch of matrices. We would like to take a more fundamental approach, a more abstract approach. And you know, so a tensor is just an element of a tensor product vector space. So I have some vector spaces x1, xk. So like yesterday, my vector spaces will be finite dimensional to avoid any topological issues, completion, all this stuff. So there will be real or complex, depending on the situation. There are some subtle differences. But in any case, we have this, a tensor is an element of this tensor product space. And k, the number of factors in this tensor product, will be called the order of the tensor. Some people call it the dimension, some people call it the size. I mean, let's call it the order of the tensor, x. And so each vector space will have its own dimension. It will have dimension d1 up to dk, and k is the order of the tensor. Okay, so let's talk a bit about this tensor product structure. What is this tensor product space? How does one think about it? So when you first learn it, I mean, it depends where you come from, but one way to think about this tensor product vector space is just to give a basis of this tensor product vector space. And basically the idea is that a basis of the tensor product is given by the Cartesian product of bases in the individual factors. So this distinguishes tensor products from the direct sums, where, you know, if you have a direct sum, you're just taking the concatenation of the bases. Now I have to take a Cartesian product. So meaning that if for every vector space I have xi, I have a basis, Ea, given I. So I is the index of the tensor factor here, and A is the index of a basis element inside xi. Then a basis of the tensor product space is given by these formal vectors, which I built taking one basis element from the first space, one basis element from the second space, one basis element from the kth space. Okay. So basically, these are indexed now by the Cartesian product of these sets of bases. Okay. And this gives you also the dimension of this tensor product vector space. It's the product of dimensions. So this is one of the important features of this tensor product, is that the dimension of of the tensor product space is exponential in K. As you know, this happens also in quantum mechanics, where if you have K qubits, the dimension of the Hilbert space is 2 to the K. Okay, and these tensor products, these simple tensor products, x1 up to xk, they are called simple tensors, and the vector space is just the span of these simple tensors. So in my vector space, I will have these simple tensors, but also sums of these guys. Okay, so you all know qubits. So qubits at C2, tensor C2, we have a basis 0, 1 for C2, and then I can build a basis for C2, tensor C2 by taking tensor product of these basis elements, and we denote them by 0, 0, 0, 1, 1, 0, and 1, 1. We drop this tensor product in between. Okay, in mathematics, if you come from mathematics, you don't learn it like this. You learn it in a more abstract, some abstract nonsense thing. So the idea comes from this. Tensors are something which render bilinear forms linear, more or less. So here is how the story goes. So I have V and W two vector spaces, and I'm looking at bilinear maps F from V cross W to Z, right? So these are maps which are linear in the first component and linear in the second component. And the tensor product is more or less the unique vector space, V tensor W, such that the following diagram commute, but there is no diagram. Let's see. Here is the diagram. So I have this map, F, which goes from V cross W to Z. It's a bilinear map. And then the tensor product is this vector space, which exists here. It's given by an existence theorem, such that any map F can be factorized through this linear space via some injective map, some injection I here from V cross W to V tensor W. And then there's this linear map now, F prime, which goes from V tensor W to Z. So basically, the idea is to replace this bilinear map F, which goes from V cross W, by a linear map F prime, which goes from, really, it's a linear map between two vector spaces. So yeah, again, this is the idea. This universal property says that any bilinear map, you can factor it like you can see it as a linear map using this tensor product instruction. But you see, it's a bit cryptic. I mean, you don't, it's just useful when you try to prove things and maybe go to infinite dimension, but the computer, and now the computer scientist perspective is just, you know, you have scalars, these have one parameter, there are numbers in some field, R or C. Then you have vectors, these have n parameters, they are indexed by something which goes from 1 to n. And you have matrices, they have n squared parameters, they are indexed by I and j. And now you have tensors of order k, they have k indices, so you have I1 up to ik, and all these indices go from 1 to n. So it's really another, you continue this list from scalars, vectors, matrices to tensors. Okay, so these are the kind of the three perspectives on tensors, like physics, math, and computer science. But I think this is the one which is the most natural somehow. Good. Okay, now let's talk about duality. As I told you, so duality is very important. So basically, the whole point of this section is to convince you that a linear map is like a two tensor. It's the same thing as an element in a tensor product. Okay, so let's see how this works a bit in detail because we'll be using this over and over again. Okay, so matrices are tensors of order 2. They have two indices, right? So so now let's look at, so usually, you know, matrices are just linear maps written in some basis. So let's look at the linear map T, which goes between two vector spaces V and W. And so the point is that the set of this vector space of linear maps, the homomorphisms between V and W, so linear maps between V and W, I claim that this is the same thing as the tensor product between the output space W and the dual of the inner space. Of the input space, sorry, V star. So how is this? Why this should make sense? Because what is a T? What does T? T eats something in V and gives out something in W. And what is this tensor product space? It's guys in W, tensor linear forms on V, so things which eat guys in V. Kind of on a logical, I mean, like from very far away, this makes sense. So let's see how this works in detail. So, you know, when you try to see something, it's better to look at an example, and let's look at coordinates. So how does this look in coordinates, right? So this map T takes a vector V, so V has these coordinates Vi, so it's a guy here in V, and gives you a vector in W, and the coordinates of the vector in W are the matrix vector product. So I'm missing a Vi here, right? There is a Vi missing here. So this is the coordinate alpha of the output of the vector T of V. And really, if you really write the matrix, this matrix T as in bracket notation, this is what you get, right? So you write, these are the coordinates T alpha I in this basis of matrix units alpha I. This is what this formula is. And this way, you see, you have written this map T as a two tensor, right? So you have something which has two coordinates T, A, I. These are the coordinates of the matrix in some basis. Now, there is a fancier way to see this. So by fancier, I mean not using coordinates, because one shouldn't use coordinates. I mean, should use coordinates as less as possible. I mean, one should avoid coordinates. The second approach, you have to look at this evaluation map. So this evaluation map, it's a canonical map. It's a map which goes from the tensor product V star tensor V to C for all vector spaces V. So it takes on this bilinear point of view. So if you have a simple tensor, a linear form and a vector, so something in V star and something in V, then the evaluation map on phi and x, it's simply you put x into phi, compute phi of x. So it gives you a scalar. So then this, going back to our map T, this output T of V, you can see it as this evaluation map, tensor the identity on W, applied to your two tensor T, tensor X. So this is a way to tell the same story, the relation between this linear map T and the two tensors multi, not using coordinates. And finally, another way to look at this is to look at really at rank 1 matrices. So rank 1 matrices correspond to unit. It's not unit, it's simple tensors. So for instance, if you have a rank 1 matrix, which is this ket bra xy, then to this matrix I associate this tensor x, tensor y hat, where now y hat is an element in V dual, something I told you about yesterday. So this element y in V, I associate it to the linear form y hat, which using the scalar product takes a vector z and gives you the scalar product by c. So this is how you associate to a vector y a linear form y hat using the scalar product. And then this leaves this, you can associate this capital T to a two tensor T. Later, when I will tell you about this graphical notation for tensors, this will become even more transparent. Okay, so we have seen that you can. So these linear maps between V and W are the same as tensors in W tensor V star, tensor V dual. And this generalizes to more than one tensor. So if you have a linear map between a tensor product of V's and a tensor product of W's, it's the same as a tensor in tensor product of W's, the tensor product of the duals of V's. Right? It's really the same thing we had before, but now we have K and L vector spaces. Okay, so this is a bit abstract introduction to tensors, but let's look at some examples. So the most I don't know if it's the most famous, but maybe the most canonical tensor that you will see, it's the unit tensor. So this unit tensor has two parameters, an order k and a dimension n. So this unit tensor will be a tensor in Rn tensor power k. And it's like the Kronecker delta. It's like this indicator function. So the coordinate I1, I2 up to Ik, so this is underline I, is either 1 or 0, and it's 1 if all the indices are 1. There is no 1 here, sorry. So if all the indices are the same, it's 1, and if the indices are not all the same, so if some of them are different, then it's 0. This is the unit tensor in coordinates. For k equals 1, what do we get? We get this, you know, I have one coordinate. So it's the all ones vector, right? Because k is 1 here. So I1, so there is no, this condition is always fulfilled. For k equals 2, I have two indices, I and j. So I get the identity matrix. If I see R2, Rn tensor 2 as n by n matrices, using the stuff that I just told you about. And for 3, for k equals 3, well, this is the tensor. It's the sum of I. These are the only basis vector which have a coefficient 1. And so yeah, so it's this 3 tensor. But now if you play this game as sometimes seeing tensors as linear maps using this duality, so this N3, I can see it, I can put a star on one of the CDs and say, well, I mean, this CD star is the same as CD using this scalar product identification. So basically what I'm doing, I'm taking this last tensor factor I, and I'm flipping it, I'm changing it from a vector to a linear form. So I'm changing it from a ket to a bra. So I get this N3 tilde. And this is something quite nice. This is this copy map. So why is this the copy map? Because this n tilde 3 takes I and maps it to II. So it takes a basis vector in the computational basis, and it gives you two copies of this basis. So this is this thing which copies classical information. But of course, I mean, this only works for the basis vectors. If you want to copy other vectors in the Hilbert space, this will not work because of the low cloning theorem. But yeah, this is the one which copies classical information. Okay. So again, we'll play this game a lot, where you like here, you see, I mean, we had this N3 living in 3 copies of CD, and we took one copy and we added a star, we dualized it, changing a ket to a bra, and then from a 3 tensor, we got a linear map which goes from 1 copy of CD to 2 copies of CD. This is something that we will do quite often. Good. Other famous tensors, the GHZ and the W states. So these are tensors of, so these are, you know, tensors, so these are vectors in C2 tensor, C2 tensor, C2. So these are states of 3 qubits. This is the GHZ one. This is maybe the standard form, and here you see that it's really this unit tensor of n equals 2 and k equals 3 up to normalization. And the W state doesn't work. So the W state is again a tensor on 3 copies of CD. So it's 001, 010, 100. So all bit strings of length 3 with just 1, 1. There's another way to see it. And maybe one important point that I would like to make here is that both the GHZ and the W states, tensors, are symmetric, meaning that they are invariant under leg permutation. Here I'm using the word leg, but you will see on the next slide why I use this word. This comes from this graphical notation for tensors. In coordinates, it means that if I permute the coordinates, if I permute these the indices of my tensors, then I will then the tensor is symmetric. The tensor doesn't change. It's invariant under this change of coordinates. So in other words, if I have a tensor in CD tensor K, then I have this action of the symmetric group, which just permutes my indices. So sigma is a permutation on K elements, so it permutes the K indices here. And if this tensor is invariant, so under the old permutation it doesn't change, then we say it's symmetric, and it lives in this symmetric tensor power, K symmetric tensor power of CD. So this is the case. This is the case here. I mean, if you see, if you swap any of the, if you permute these three indices, you will get the same tensor, and the same for GC. Okay. So these are symmetric tensor, and of course you have also the anti-symmetric ones where this action here you get the -1 to the power the sign of this permutation sigma. You have the same story. Okay, good. Now something very, very cool. It's this graphical notation for tensors. This is something that it's very used nowadays, and it's very the problem with tensors is that you have many indices. So sometimes when you do computations, it becomes cumbersome to handle all these indices. And Penrose has invented this graphical notation for tensors, and since it has been upgraded and maybe extended to cover many scenarios, so this is what I'm going to talk about next. Okay, so basically I borrowed this presentation from this, I gave it the reference at the beginning of the talk. There is this very nice blog post by Jordan Taylor where he describes in detail this graphical presentation, but there are other sources. So there is also this very nice paper, Hand Waving and Interpretative Dance, an introduction course on tensor networks, where this also is also discussed. But basically, if you look at any paper in tensor networks, they will introduce this. Just choose the one you like. So the idea is that to tensors, we shall associate some shapes. So here there are these small gray disks. And to coordinates, to these indices that index by tensors, I will associate these half edges sticking out, these legs that we call legs that stick out of the shape. For instance, a number doesn't have an index; it's just a scalar, so there is just the shape without a leg. A vector has one leg, and morally you can think of as these coordinates sitting on this leg. So if I put an I on the leg, I just get the coordinate VI. A matrix has two legs, I and J. So there is one coordinate here, one coordinate here. And 3 tensor has 3 legs, I, J, K. And you can think them as, usually people represent 3 tensors as cubes. And sometimes they like to think that it's really like a bunch of matrices stacked one behind the other or something like that, etc. So if you have a tensor of order K, you will have a shape with K legs. Okay, so this, since I borrowed this from this guy, from this blog post, so he also talks a lot about PyTorch, how to implement these things, and he gives you some, this is syntax in Python in this PyTorch library.
Why is
so these are the dimensions. You mean it should, because it should be, you should have 5 elements here?
No, I don't know. Yes.
It's a good question. Ask him. I'm sorry? So this is just Jordan Taylor. I don't know him in person, but he writes very nice introductions. Yeah, so don't ask me about Python syntax. I don't know how this works. Good. So exactly. So now, if you really want to get an element from this tensor, you can if you get the element 0 to 0 of this tensor, you just put 0 on the first coordinate, 2 on the second coordinate, and 0 in the third coordinate, and then you will get the element 0 to 0 of this cube, which has some value, some numerical value. So this is like accessing your tensor in some specific position. Okay, so again, there is the story that tensors have exponential number of components in K, and So somehow, if you want to describe an exponential, like an object of exponential size, it makes sense to decompose it into simpler objects. And this is where this graphical calculus becomes very, very powerful. Because we can build larger tensors from smaller tensors. That's kind of the idea. Okay? So before we had these shapes with legs, with these half edges sticking out of them, and now we will connect these half edges between two tensors. So this is how the dot product, so the scalar product between two vectors, I have two vectors A and B. If they have this edge now, so you see this is a full edge, there is nothing sticking out. So whenever you have a full edge, you should think that there is a sum on the index which sits on this edge. So here I have the sum over I, so I get just the sum of the ith coordinate of A times the ith coordinate of B, so I just get the scalar product between A and B. And the result is a scalar because this object here doesn't have any legs sticking out, so it's a scalar. So half edges means legs sticking out, so this means that your object lives in a tensor product, and these full edges, these contracted edges, means that you have a sum. So this is the opposite thing you could do with two vectors. You can build this ket bra. So this now has two legs sticking out. So this is a matrix. And you see it's the ket bra, so it's the matrix which has coordinates AI, BJ. Because I haven't contracted these two legs. Now here you have the matrix vector product. You have a matrix Aij times a vector Bj. So you see this edge here is contracted, so I have a sum over J, and this leg is not contracted, so it stays. So what I get is a vector Y, which has coordinates Ya is sum over J, Aij, Bj. So it's really, this Y is really the vector A times B. Right? So this is how you compute the matrix product vector A times B. Right? So I hope you get the idea. This is the matrix product. You have two matrices, capital A, capital B. You multiply them, you sum over J, I and K are free, and you get this matrix Y, which is the product AB. And the trace, now there is no free legs, so this diagram here corresponds to a scalar because I don't have any legs sticking out. And I have two indices here, I here and J here, and I sum over them. And what I sum is Aij, Bji, and here you recognize the trace of A times B. Okay. So this is how you can write this simple matrix product, matrix vector product, all this stuff using these tensor diagrams. Okay, so again, the main takeaway is that these contracted edges correspond to sums, and legs sticking out correspond to the fact that the object you are describing here lives in a tensor.
Good question.
Sure.
This is for real numbers.
Yes.
Simple rule when these are complex.
Sure, it's exactly the same rule. So being complex or real, so this can also be complex numbers.
Or you have to put complex conjugates in these coordinate terms.
So yes, so good point. So if I really want to write, let's look at this, what he calls outer product. So this diagram here, so if I really want to write a tensor diagram for this object here, where A and B are in CD, then this will be really A, and here I'll have to put a complex conjugate. Okay, now we can go crazy. We can have much more complicated diagrams because, of course, linear algebra, we don't need tensor diagrams, but tensor diagrams are nice when you have big tensors. So for instance, this picture here, what does this correspond to? So basically here I have three tensors. I have a blue one, a yellow one, and a green one. You see they are all of order 3. They have 3 legs sticking out. And some of them are contracted, some of them are not contracted. any case, what we can already say without looking into too much detail is that the answer of this diagram here, represents a matrix, because I have two legs sticking out. And the diagram tells me what are the coordinates of this matrix. So the coordinate ij of this matrix is the sum over all these contracted edges. So I have alpha and beta because I only have two contracted edges. And so it's really the blue tensor coordinate I alpha beta, the green tensor coordinate beta, and the yellow tensor coordinate j alpha beta. And the result is a matrix. So basically the idea is to replace this formula here by this tensor diagram here. They're the same thing. So whenever you see a tensor diagram, you can always go back to the formula. You should do this the first 5 times you see them, but then you will see you will prefer these to the formulas. And basically you have to do this translation until you're comfortable with it, and then it will be very natural. Okay, so basically these are used a lot in tensor network theory, because when you have like awful sums like this, you can represent them simply as this very nice object here, which disappears. For instance, if you have some model on a lattice, you might have to consider at some point you might have to consider such formulas, and it's much nicer, and you get much more intuition and more maybe meaning from this diagram than from this sum over indices from I to U. This is kind of the idea. The idea is to replace long formulas with many indices by pictures, but they're the same thing. So doing a proof with pictures is as rigorous as doing a proof in coordinates. Okay, so now there is a question. For instance, this diagram here, this represents a number, right? This is a scalar number because there are no legs sticking out. Right, so this is just a number. It's the sum that was above. Okay. So the input is, you have these tensors. Some of them are matrices. So A, V, Z, and E are matrices. They only have 2 coordinates. B, C, D, X, Y, W are 3 tensors. They have 3 coordinates. And the question is to compute the sum. And how should you do it? I mean, naively, you just write for loops and compute the sum. But actually, this is a very important problem because not all ways of computing the sums are equivalent in terms, you always get the same result, of course, but there are smarter ways to compute the sum such that you have less computations. So, and here's a question for you. Maybe a simpler one. I give you n matrices, x1, xn. They are rectangular matrices. So xy has dimensions di, it's dy times di plus 1. Okay? So they are rectangular matrices. The dimensions match, so I can multiply them. So what's the most efficient way to compute the sum? To compute this product, x1, xn. How should I do the multiplications? Because, so basically, when you do multiplications, you only know how to do matrix multiplication, so you have to do them in some order. For instance, maybe I can multiply x1 to x2, then the result with x3, then the result with x4, etc. Or I can start in the middle and then do the multiplication to the outside, or I can group them 2 by 2 and do kind of this tree thing. And if you sit down and you write how many operations you need to perform to compute this product, you will see that depending on the way you put the parentheses, you will not get the same answer. So what's the best way to multiply matrices? Is there like a nice way to think about this? Well, the answer is yes for matrices, but no for general tensor networks. In the sense that there is it's very hard to find the optimal way to contract to multiply these tensors for a general tensor network. So it works for trees, like in this case of matrices, this is like a line, it's a tree. But in general, it's a very hard computational problem with lots of implications for people doing these tensor networks things. So something that they think a lot about. What's the optimal way to compute these sums? And the more non-tree like your tensor network is, the harder it is to find this optimal. Okay, so let me go back to this unit tensor I told you about. So I would like to represent my unit tensor by a dot, by a black dot. And with k legs sticking out of it. So for instance, this all ones vector will be just a dot with one edge sticking out of it. The identity matrix, the unit tensor of order 2, just a dot with 2 lines, but this is, I can just represent it like this. It's, it requires that the 2 indices coming at both sides to be equal. And the copy tensor, I will represent it like this. Actually, you see this thing already appeared in disguise. I don't know if you saw it in this diagram. It was implicitly here, right? Because I told you that I can construct edges, but this is not an edge, it's like a hyper edge, but it's precisely the fact that this beta appears 3 times. So it's like here I had this copy tensor associated to beta. So usually people don't write it, good. Okay, so let's start doing some more quantum info stuff with this graphical notation. Let's look at the maximal entangled state. So this maximal entangled state in CD tensor CD, we call it by ket omega. It's this vector. It's sum of II 1 over square root of d. So you see it looks like this unit tensor. For qubits, it's the 0, 0 plus 1, 1 vector. And graphically, I represent it as really as the unit tensor, right? So this omega, the box, now I will draw like rectangles. It's a 2 tensor, so it has 2 legs sticking out of it. Basically, the only condition I have is that the indices here, I and j, should be the same. So this is why I draw this edge here between I and j. Or if you prefer, it's really the picture you had at above. It's really this identity. It's the same as the identity matrix, right? You need the 2 indices to be equal, but the identity matrix is something which lives in a vector space tensor its dual, whereas this maximal entangled state is something which lives in V tensor V. This is the picture for the maximal entangled state as a vector. Now, if I look at the maximal entangled density matrix, so this is the projection on my maximal entangled state. So this is small w, it's the ket bra omega omega. It's this matrix. The way I will represent it is now, I have a copy of omega here. I have the adjoint copy of omega. So I flip the things in order to indicate that this thing here, it's vectors. So it's a bra, and this thing, it's out vectors. So it's a ket. But in any case, the picture is this. So let's do something with this graphical notation. Let's show that let's compute the partial trace of this omega. So this is my omega. So let's say I want to compute. I'm not sure, maybe I should write a bit. Okay, so let me compute the trace over the second Hilbert space of this omega, the partial trace over this one. So in graphical notation, how should I depict the partial trace of this vector? I should close one loop, the second one, right? Because this is really identity on the first guy, tensor the trace on the second, right? So I leave my first set of legs on the first factor, on the first copy of MD, of matrices, and on the second copy of MD, I take the trace. Okay. So let me plug the formula for omega. So you see, the answer will be just one matrix because I only have now 2 legs. So it will be one, it's always one matrix, but it's a single partite, it's a 1 partite matrix. So I have these 2 legs. So this is 1 over D. This picture. And this is the identity. So this is a very trivial computation showing that the reduced density matrix of a maximally entangled state is a maximally mixed state. Okay. Using this graphical. Good. Okay. More examples. The matrix multiplication tensor. So this is like my favorite example of a tensor, and many people's favorite example of a tensor, because there is a big conjecture related to this tensor that I will briefly mention. So what is this matrix multiplication tensor? It's a tensor which encodes matrix multiplication. What do I mean by this? So I have two matrices, rectangular matrices, A of size m times m cross n, B of size n cross p. And this matrix product CAB it has coordinates, so it has coordinate as you know. So what is the matrix multiplication tensor? First, let's look at matrix multiplication. It's a bilinear map. So the map which sends A and B to C, to their matrix product, it's a bilinear map which goes from m cross n times n cross p matrices to m cross p matrices. So it sends the A comma B to the product AB. So as you know, any bilinear map, I have a tensor. That's the point of tensors. They linearize bilinear maps. So this is the definition. So this is the definition of the matrix multiplication tensor, the MAMU tensor. So the MAMU tensor, what does it do? So it's a tensor. It's a three tensor. So it lives in the dual of the first matrix space, tensor the dual of the second matrix space, tensor the output matrix space, right? Because it eats an A, a B, and it spits out a C. Okay? So to this map here, which is given in coordinates by this formula, by the formula you all know, I will associate this tensor here, the MAMU tensor, which lives in this tensor product space. So again, what does it do? It gives you, it's this formula. So what I claim is that this formula is the matrix multiplication. What do I mean? I mean, what I claim is that this formula is the same as this formula. Meaning that you see, I'm computing the IK coordinate of C as a sum over so this is a linear form on matrices. So this map here, EIJ dual, takes a matrix A and it gives you AIJ, right? It's the linear form on matrices. And the same for the B matrix, and I'm summing over all IJK. In this way, I get all the components of my matrix C as a sum over J of AIJ times BJ. Okay, so this is a bit. I mean, it's not very. I mean, it's kind of you have to. It's a bit abstract because you know there's all this notation, these vector spaces, this tensor product, but this and this are the same thing. That's what I want you to think about for a moment. So this is kind of one cool thing about tensors is that any multilinear operation you might want to do, you can encode it in one object. Right? So this MAMU tensor, it's not any of ABC, it's really the operation of matrix multiplication. It's how you compute the coordinates of C in terms of the coordinates of A and B. It encodes this formula, the formula you have learned from matrix multiplication. Okay? So this works for rectangular matrices, and whenever I have the same matrix, I will just use I will just write a MAMU n when I multiply two n by n matrices to get an n back. Okay, so I told you that this matrix multiplication tensor lives in this tensor space here. So it's a three tensor. It takes dual of a matrix space, dual of a matrix space, a matrix space. But remember from the very beginning that matrices are nothing but tensor products of a copy of the vector space of the, so it's a tensor product between the output vector space and the dual of the input vector space, right? So M cross N matrices are nothing than Rm tensor Rn star, okay? So something which eats a vector of size n and gives a vector of size m. So now, since this wasn't already too complicated, I will replace every copy of my matrix vector space by this tensor product. I'm taking care of the duals. So now, what I want to tell you is that, what I want to infer is that this Mamu tensor is actually, in disguise, a 6 tensor, a tensor for the 6, because every matrix space, you know, I can compose it as in the basis vector space, and then Mamu tensor now has 6 tensor factors. But yeah, this shouldn't come as a surprise, because if I go back to my bracket notation and I write this formula, you remember I had Eij star, Ejk star, Eik, and I write this in bracket notation. Then you see I have basically, this is also, I can put a tensor product here. The brass corresponds to Rm, Rn, Rm, and the kets correspond to the dual spaces. So I have 6 tensors here, and you see I can bunch them, I can permute them. So you see I can take this I here, this bra I here, and the ket I here, and I can sum over I separately, I can sum over j separately, and I can sum over k separately. So the conclusion is that, you know, the sum over I from 1 to m of I, this is just the identity. So the conclusion of this computation is that my Mamu tensor is just a product of a tensor product of identity matrices. So actually, it's pretty simple. So matrix multiplication is a tensor product of 3 identity matrices. That's the conclusion of this thing. So this looks, of course, this is very simple. Why people are excited about this? Because there is a warning. And the warning is that the this tensor product here and this one, so the last 2 formulas are the same. So these 2 tensor products are not the same as these 2 tensor products. Because you see, here I permuted the i's, right? So here the I was in 2nd position. Now this, well, I took the one which actually coincides. So the ket I was in 5th position here, and here it's in the 1st position. So I have permuted some of my tensors to write them as a tensor product of the identity. But still, this is correct. So depending on where you choose to split to put the tensor products, you can have a really simple formula, like a product of 3 identities, or you can have something which is more complicated, which encodes the rule for matrix multiplication. All right, so these are coordinates. So let's look at some pictures. Okay, so on the top here, you have the rule for matrix multiplication, which you saw already, right? When I talked about these graphical calculus, right? So C is A times B. I'm just contracting these legs of A and B. And now what I want to do, I want to encode this matrix multiplication using a tensor, the Mamu tensor. So this is a beast which has 6 legs. And when I put A here and B here, I should get C, right? Remember this bilinear idea of matrix multiplication. It's something which eats a matrix A and B, and it gives out the product C. So I want this box here to encode the operation above. The question is, what should I put in this box such that this diagram and this diagram are the same? You see, it's easy. I mean, you just have to connect the wires in the right way. The question is, can I make everything fit in one page? So see, this is the diagram, which that if I put this here, I get precisely the first picture, right? Because you see this, for instance, let's look at this. Let's look at I mean, you see, you get, if you put A here, you will get this here corresponds to the matrix multiplication, corresponds to this leg here. This one would be this one. And then you get C, you get the matrix. Okay. Makes sense? So now you can see graphically, without any coordinates, that really the matrix multiplication tensor, if you separate it correctly. So the way the matrix multiplication tensor is defined, the tensor product structure is I have one vector space here corresponding to A, one vector space here corresponding to B, and one vector space here corresponding to C. So this is the way I split. I have something here, and something here. It's a 3 tensor. But if I want to see it as a tensor product of 3 identities, you see the split has to be different. I have one vector space here, one vector space here in the middle, and one vector space here. So this is what I meant on the previous slide when I said, depending on how you split your 6, how you package your 6 legs into packets of 2 to get a 3 tensor, you get either really the matrix multiplication tensor acting on 2 matrices and giving you the product, or identity tensor, identity tensor, identity. Are there any questions about this? Because, I mean, this is kind of matrix multiplication and also this graphical thing, so it's a good ask if there are questions. Okay. So now let's switch gears. Yes. It actually doesn't help. I mean, it helps because you know that, for instance, you know that the coordinates of, for instance, the coordinates of these tensors are either of the Mamu tensor are either 0 or 1 because it's just tensor product of 3 identities. But the way they are packaged, the way you package as a 3 tensor, as you use it for matrix multiplication, has nothing to do with this tensor product of 3 identities. It's just that if you factor the legs in a different way, you can see 3 identities, but this is not the way you should factor the 3. You should package your six vector spaces to get matrix multiplication. It's just an observation that a tensor which looks very simple in certain way of parenthesizing your 6 vector spaces gives you the rule for matrix multiplication. So it's something which is not at all trivial. So if I print the coordinates, they are the same numbers. But the way I would like to look and to use my my Mamu tensor, for instance, if I want to use it as a bilinear map, taking 2 matrices and giving the product, then the identity tensor identity is not the correct way to package it. Right. So so the Mamu tensor is this picture, right? But now assume that instead of doing like this, I will package it differently. So this is that picture rotated a bit, right? I mean, I still have 3 identities, but now, you know, I just wrote it differently. So if, let me write it again. How it is. Okay. So so think about this vector space here. I can call it A output. C output. Okay. So this is how it works for matrix multiplication. This is how the tensors should be called, right? I mean, here I put my A, here I put my B, and I get out the C. So this is the same picture, but now these things get shifted. For instance, I have, let's see. You know, I can copy, right? I have A output here, C output here, A input, B output. and I'm left with this one. C input, B input. Okay. So these are the same object, but I have permuted my tensor. So if I were to put A and B here, like I did before, then this thing will give me what? So let's call this operation here an operation psi. So psi of A and B will be trace of A, trace of B, times this maximal entangled state. So it's not at all matrix multiplication if I use this picture. But if I use this picture, I get matrix multiplication. So one has to keep track what space does what. I mean, that's the. So this tensor here, if I plug A and B, I get this formula. Whereas here, if I plug A and B, well, if I plug A and B here, you see what I get is really AB. So if I can write identity here. Okay, so this box here implements matrix multiplication. This box here implements this operation, takes the trace of one input, trace the second input, and use the identity. So yeah, the point is that you have to keep track which tensors corresponds to, which legs corresponds to A, which legs correspond to B, and which legs correspond to C. And if I rotate them to get this very nice identity, tensor identity, I lose this.
Question here.
Yes.
Yeah, so I just in the rotated picture also, I could have actually like kept track of the correct indices and joined correctly, no?
Of course, of course. Let's see how to do. I have to put, so if I have A here, B here, so you have to do it. So let's see. So I have to put, I don't know, maybe if I put, so this A should go here. This maybe should go here to do the product. The B should go here, and this should go here. Of course. But, good. No other questions, then let's. Good. So now let's talk about entanglement, as I promised, right? And this will be the last topic for today. I talk about entanglement of pure states, and I'm going to look at multipartite pure states. So let me get rid of this pointer. So I'll consider a Hilbert space which is a tensor product of k Hilbert spaces. So this is what I call multipartite because k can be more than 2, it can be 3, etc. And a vector psi inside H is called separable if I can decompose it as phi1 tensor phi2 tensor phi k. If I can write it as a tensor product of vectors in individual spaces. And if I cannot, it's called entanglement. Okay. So vectors which I can decompose separable, which I can decompose like really a simple tensor are separable. And if I need to write it like a sum of these guys, if I cannot just have one term in the sum, then they are called separable. Okay? So of course, people want to know how to measure, like to have a measure of entanglement. So how far from being separable a given tensor is. And today we'll talk about two ways of doing this, two measures of non-separability of entanglement. One will be discrete, will be an integer valued, this will be the tensor rank. And the other one will be this injective norm. And this will be the first example of tensor norms we'll see. Good, let's start with the rank. So it's clear that any element, any vector in any tensor in a tensor product can be decomposed as a sum of simple tensors. And the rank is simply the minimal number of terms in such a sum. So the rank R, R of psi is the minimal R, such that my psi can be written as the sum of R tensor products. Of course, if you're separable, then it means you can write it like just a tensor product, so R is 1. And for entangled vectors have R equals 2, 3, or more. In the bipartite case, K equals 2, so if I just have two tensor pairs, then again, always when you have a 2 tensor, think of a matrix. That should become automatic by now. So always my vector, my tensor psi, maybe let me write it here, since now we have this tool, this graphical calculus. So whenever I have a psi, so psi is a 2 tensor. So it's something which has 2 legs. Okay, this leg corresponds to H1, and this leg corresponds to H2. So whenever I have such a psi, I associate, and it's a one-to-one correspondence, to a matrix now, psi, capital psi, which is the same thing, meaning that this object here, it's just a vector psi, and I do this. Okay. So basically, what I'm doing is that this H2 here, I'm seeing it as, I'm putting it on the other side. And this equality here, this just means that this H2, I'm identifying to its dual. Right? Because here psi was a vector in H1 tensor H2. And this matrix, capital psi, is something in H1 tensor H2 dual. So this is the same as, so this means that psi is a map which goes from H2 to H1. It's a linear map. Vice versa, to matrix psi, I can associate the vector psi, which is and if you really want to go to quantum information ideas, then this vector psi, so this lives in H, let's take H1 equals H2 equals CD. Then this is nothing than psi okay. You see, this is psi tensor the identity. This psi operation tensor the identity, and this here is omega. So this is this isomorphism. So a matrix is like a 2 tensor, and you have to be able to go back and forth between these two things. People call this, so people call this the vector, like the vectorization of the matrix. Many names. It's used all over the place. Okay, so think about it. Think about this rank, right? So the rank of the tensor is the minimum number of R, such that I can write psi as sum, let's say alpha I tensor beta I. Okay. But what I'm claiming is that this is nothing than the usual rank of the matrix capital Psi. What is the usual rank? It's the minimum R such that I can write my matrix as a sum of rank 1 operators. So this tensor rank for matrices, it's just the usual rank. Okay. For our favorite tensors, the GHZ and the W, they have actually, so let me go back and show you the formulas. Find them. So the GHZ, from this writing, you have a decomposition of GHZ as a sum of two tensor products, right? That's one, that's the second one. So from this formula, I already know that the GHZ has rank at most 2 or less. The question is, can it be less than 2? Can it be 1? Can I write GHZ really as a simple tensor? It's quite easy to see that you cannot. So the rank of GHZ is 2. And this is like the optimal decomposition for the rank. And the same for W. So here you have, this formula here tells you that the rank is 3 or less, because I have a decomposition with 3 terms. Can it be 2? Can it be 1? The answer is no. Actually, you can. It's really an easy exercise. So the rank of GHZ is 2 and the rank of W is 3. So this rank is, for matrices, is the usual rank. We can compute the usual rank by doing this Gaussian elimination. However, for tensors, it's a hard problem. It's NP complete to compute the tensor rank. So to show that if I give you an R to decide whether the tensor rank is R or less, this is NP hard. So it's difficult to compute ranks for tensors of order 3 and more. Here's something very interesting. The rank for matrices, I mean, that really distinguishes matrices and tensors. Something happens when you go from tensor of orders 2 matrices to higher order tensors. So let's think about this question, whether, let's look at the set of matrices with rank R or less. So what I claim is that this is a closed set for matrices. Why is this the case? Because a matrix has rank R or less if all of its principal minors of size R plus 1 are 0. That's almost the definition of the rank. The set of matrices with rank R or less is closed, and this is not true for tensors. And we can see it from our favorite example, the GHZ and the W states. So if you think about, think about this formula, look for a minute at this formula. Try to convince that this is correct. So I'm claiming that W is the limit when epsilon goes to 0 of this tensor here. So what happens here, you see when I expand this tensor product 3, I get 0, 0, 0, which cancels with this one. And then the order 1 in epsilon, I get 1, 1 and 2 zeros. So this is exactly like W. The only terms in this expansion, I have 27 terms. One is 0, 0, 0. And the ones which have epsilon, which are order 1 in epsilon, are 0, 0, 1, 0, 1, 0, and 1, 0, 0. So they contain only 1, 1. So it's a double. So what I've shown is that, so this guy here, the tensor here in the limit, this is a tensor of rank 2. At most 2, because it's, it's a sum of simple tensor, simple tensor. So this means that I've written my W, which is a tensor of rank 3, as a limit of rank 2 tensors. So this means that tensors of rank smaller than 2 are not closed. This is something very problematic for people it's problematic. It makes the theory rich. because you can now you can go to people in algebraic geometry think a lot about these questions. So now there is something which is called there is a new notion of rank called the border rank, which really includes these limits. So the border rank is the minimum R such that you can write your tensor as a limit of tensors of rank R. So it's the kind of the closure of this rank R. And so basically for tensors in general, you have many, many notions of rank. Whereas for matrices, you have just one. And this happens with other notions, other things for tensors like singular values, norms, many, many things, where there are many different notions for tensors, and for matrices, they collapse to the same number or to the same quantity. Somehow, Joseph Landsberg says that matrices are a degenerate case of tensors. So really, tensors are like what's normal, but matrices are kind of too simple, so they are degenerate. But yeah. Okay. Let's go back to our favorite tensor, the matrix multiplication tensor. So let's take M and all the matrix dimensions to be the same. M equals N equals P. And remember, the rank of the Mamu tensor is the minimal R such that you can write your tensor like this with the factoring corresponding to matrices. So with this factoring, right? So the factoring here. So this is the U is a vector here, the V is a vector here. So it's a matrix actually. This is a matrix here, and this is a matrix here. So with the correct factoring of the Mamu tensor, not the identity tensor, Exactly. So this is this picture. And actually, you can write the point of this picture is to show you that the rank computation can be seen graphically, right? Because what I'm doing, if I package my vectors Ui into a matrix U, capital U, the same for V and the same for W, then this decomposition here can be written via this unit tensor as follows. So it's just U tensor V tensor W applied to this copy tensor, if you like, or this unit tensor of size R. Because the sum over the index here, it's precisely the sum here. Right? And this, when I put I here, I get small wi, small ui, and small p. So this picture and this formula are the same. So the question is, what is the rank of this matrix multiplication tensor? The first claim I want to make is that this rank of the matrix multiplication tensor is precisely the number of multiplications you have to do when computing matrix product. Why is this? Because every term in the sum, well, I mean, here it's a n equals 2 case, but it doesn't matter. It's a linear form which gives you a coefficient of A, a linear form which gives you a coefficient of B. You take the product of these two coefficients and you put the result into some position ik of C. So every term corresponds to doing one scalar product, one multiplication of numbers in the matrix. Right. So this is a picture, I'll tell you later, this is a picture from this alpha tensor paper, where they really show you the matrix multiplication tensor for n equals 2, really as a tensor, as a cube. So here so this is the formula, and basically what this says that, you see, the matrix multiplication tensor of order 2 is a tensor of order, 4 times 4 times 4. So it's a cube of size 4. And the black indices here, so the black small cubes inside the big cube, correspond to ones, and the transparent one corresponds to 0. So this thing here tells you, for instance, so you see I have a 1 in position, in position, I don't have the A's, maybe because I haven't scrolled enough. Can I have everything on one page? That's the question. Okay. So for instance, how do we see that C1 equals A1 B1 plus A2 B3? So the fact that I have to put A1, B1 into the coordinate of C1 is precisely this one here. And the fact that I have to put A2, B3 also in the coordinate of C1, it's precisely this dot here, because you saw it has coordinate A2, B3, C1. So this is maybe a graphical way to understand the usual rule for matrix multiplication. So in this decomposition, where really I write this decomposition here of the MAMU2 tensor, this tells me that the rank of the MAMU2 tensor is at most 8, right? Because I have written it as a sum of 8 guys of rank 1. And Strassen made this breakthrough that actually this rank is at most 7. So he found a way to multiply two 2x2 matrices using only 7 multiplication. Equivalently, he found a decomposition of the MAMU2 tensor as a sum of 7 terms of rank 1. So here you have the algebraic formulas on how to compute C1. So first, you have your matrices A and B, you compute all these products, you have 7 of them, 7 products. Sums are free, sums don't cost anything. So I have 7 products, and then I can compute my entries of C's as sums or differences of these 7 products. And this thing here is the same as this thing here. So this, these are these matrices U, V, and W. You see these are matrices of size 4 times 7. So this shows that actually the rank of MAMU2 is at most 7. So I can multiply 2 2x2 matrices using only 7 multiplications. Later, Vinograd showed that it's actually 7. You cannot do it with 6. So why is this extremely important? Is that basically now if you have this by 2x2 matrices, I mean, that's not a big deal, but now this extends, by chopping matrices in 2x2 blocks to matrices of size n. So usually if you want to multiply 2 matrices of size n, you need to do n cubed multiplications using the usual algorithm. But now using Strassen, you only have to do n to the power log 7. So this is like 2.8. So this is log base 2. I mean, so this is very important because matrix multiplication is like the thing which is in every algorithm. So if you can gain at this building block a bit, that's great. And this improvement was obtained only by thinking about multiplying 2x2 matrices. You can think maybe if I chop them in blocks of 3, or if I chop them in blocks of 4, I can do even better. I can lower this exponent here. And this is what a large part of the algebraic complexity theorists do. They try to lower this number. And the notion is this asymptotic rank, which also has application in quantum information theory, but I won't go into this. So it's kind of the same idea. So I have my tensor T, and I want to compute the rank when I take n copies of T. Right? So I will take n copies of T, I will compute the rank, and then I will take an nth square root to kind of make this an interesting quantity. Here I have to be careful because I told you that when you have the tensor, so this is the Kronecker tensor product. It's a different tensor product, meaning that if I have 2 tensors, S and T, usually when I talk about their tensor product, I want to say that S tensor T lives in is a tensor of order 2k, right? Because it will have 2k legs coming out, k from X and k from T. But if I package corresponding space, so if I package x1 and y1 and call this z1, and xk and yk and call this zk, then S tensor T will be a tensor still of order k, and I call this the Kronecker product. So basically, the Kronecker product is the usual tensor product, but then I package by 2 the spaces. And now this asymptotic rank of MAMU2, it's this omega. log of the asymptotic rank. So this omega is what? This omega is basically how fast can you multiply n by n matrices? That's the kind of the question. So it's the rank of MAMU n. So this behaves like n to the omega, where omega you can only look at MAMU 2, but you have to take this asymptotic rank. Something you can play with these ranks, show that they are sub-multiplicative and all this kind of stuff. But kind of the question is, what is the how fast does rank of MAMU n grow with n? I will stop here. So yeah, this is the picture taken from a very nice paper in Quantum magazine. So the classical algorithm is n cubed. Strassen found this rank of MAMU 2 is 7, so he lowered it, and then people lowered this rank. And you see, I mean, now there are improvements at the 5th decimal, I think, place. So there are papers which improve the 5th decimal of this omega. It's really something very, very fundamental. And people think it's 2. So people think you can multiply n cross n matrices in time which is n squared plus epsilon. So they think that this should be 2, but it's kind of like one of the most important open problems. So to conclude, I talk about this rank of a tensor. So in respect with the entanglement, it's kind of a discrete measure of entanglement. So separable states have rank 1, entangled states have higher rank. And I try to show you that this rank kind of is different than the matrix case and something which is hard to compute in general. And next time I will talk about tensor norms.
Thank you very much. Questions?
Thank you. Thank you for the talk. So I have two questions. One is does this rank have to do anything with Schmidt rank? And yeah, first that question.
Let me answer this. So the Schmidt rank of this psi here is, so this is precisely the Schmidt rank. But if you want, I can put cats. So let me write the Schmidt decomposition. So this is the Schmidt decomposition when I ask for orthonormal bases, but it's the number of non-zero Schmidt coefficients. It's the same as the rank. Here in the rank thing, I don't require that. In the rank definition, I don't require that this to be orthonormal basis. But for matrices, it's true. You have the same property that I can find a decomposition with rank of my matrix terms, such that the things are also orthonormal basis if my matrix was a Hermitian to begin.
Second, I have one small doubt, like when you defined duality, isomorphism between this V and W.
Between Z and
vector spaces V and W.
Yes.
Yeah, so there you had defined like this isomorphism goes from VW to V tensor product, W tensor product V star.
Where was this?
Very start.
Maybe here or even before?
Even before, yeah. At the very start. Yeah, here. Yeah. Yeah, so
here?
So the general definition below, it had like, so it goes from K to 2 times K, so, or L times K. L plus K.
L plus K, yes. So,
yeah, L plus K. So
the point is, my map, the linear map capital T, has K input spaces and L output spaces.
yes.
Right? Because you read from right to left. And I associate to this T thing, which has L output spaces L plus K, right? So these are my L, these are my K, and this is just, this T.
Yes, but when you went to this unit tensor example, there I think it was not L plus K, right? It was less than that. So
Let's see.
shouldn't it be 3 plus 3 unit tensor definition?
This is afterwards.
Yeah, afterwards, yeah. Yeah, so this tensor, copy tensor, it's not
Yes.
3 plus 3, right?
So the rank, so this goes from 1 copy to 2 copies,
Right.
and the tensor is in 3. So the D is a dimension of each leg, right? But here you have the linear map which goes from 1 copy to 2 copies, and the tensor itself has just 3 copies. So this 1 plus 2 equals 3.
I see. Okay, thanks.
So D, I mean, these D's could be different. I mean, the D is the dimension of each leg, it's not the number of legs, right? So the D is called the dimension, and the K, here K equals 3, it's called the order.
Oh, I see. Thanks.
Thanks. Further questions? Well, if that's not the case, let's thank the speaker again.